Hariom, all of you. I've always been on this side whenever I have come to Sandipani to attend some sessions or to listen to some talks. It's a great pleasure for me to come here and interact with all of you. I'm sure your course is going great and all of you have had some exposure about Prarabdha. So now you know it is true. Those of you who thought I had left math long back in school, right? And Swamiji's Prarabdha is over, so he doesn't have to attend this session today. Something else came up, right? So on that lighter note, we'll just start. And the idea of today's interaction is to give some overview about what happened in mathematics in the Indian subcontinent over the last few thousands of years. And I'll be very happy if you would want to stop me at any point of time, ask questions or whatever. We can make it as interactive as possible. Right, so there is a pun in the title. I hope you could see that. Not generated by ChatGPT. I made this on my own. Okay. So what does nothing refer to over here? Zero. And what does place and value refer to? The place value system, the decimal place value system that we use, right? Okay. So let's start. Let's start with maybe just a quick, whatever icebreaker or whatever you want to call it. What do you think was India's contribution to the world of mathematics? If you can just pop up whatever, pop out whatever you have heard about India's contribution to math. Names for extremely large numbers, very true. In some way Indians were fond of huge numbers, big numbers. Trigonometry, zero definitely. Geometry, algebra, these branches of science, number theory, okay. But weren't other civilizations also talking about these area of mathematics? I mean, what is special about India's contribution to mathematics, right? I mean, we had great civilizations like the Greeks, the Babylonians, Chinese, Mayans, Roman civilization. Everybody did something or the other in math. So we'll just try to see some idea about how Indian mathematics is slightly different from these civilizations, okay. This is something that I just want to, put on the first slide. Generally when we talk about ancient Indian, we tend to put everything into one bucket, this happened long ago. But that long ago is not just one point, but it is a linear scale, right? It's spread over thousands of years in any civilization. So when we say Indians did this, it was not one particular point of time, it was on a scale. So it is very important to see where do things fit into the scale. So in some slides I have put up a timeline on the top, so you can see where that event is happening from a historical timeline perspective, okay. So we'll start with this. I have divided the session into a few sections, starting with Sulba Sutras. Have you heard of Sulba Sutras? Sulba Sutras were part of something called as Kalpam. Kalpam, I am sure you have heard by this time, right? Kalpam is one of the 6 Vedangas, right? Shiksha, Kalpam, Vyakaranam, Chandas, Niruktam, Jyotisham. When we look into the Vedangas, from your experience and exposure so far, can you give me some insights into which areas do you think mathematics come into? Which of these Vedangas contain mathematics? I thought you will say Kalpam first because so Jyotisham, of course, Kalpam, Chandas, more or less, I mean that's quite intuitive, right? What about Vyakaranam? Where is grammar? We wanted to learn grammar, not mathematics. But we see that we see, I mean, this has been my experience and exposure, okay. There might be math in Shiksha and Niruktam also, but I haven't studied those disciplines at all. Even the others I have just touched upon, but in these 4 Vedangas, we see strong application and appearance of mathematics, okay. Right. So, starting from these Sulba Sutras, Bodhayana's Sulba Sutra is the oldest known mathematical text, or rather I wouldn't say a mathematical text, but a text that covers rules for geometric constructions or rules for doing construction for fire altars, okay. And there were some 7 Sulba Sutras that are famous and known, out of which Bodhayana Sulba Sutra is the oldest. It is estimated to be around 1000 to 800 BCE, which is like about 3000 years ago, okay. And in that, what did they discuss? They discussed a few things like construction of fire altars. Has anyone seen these kind of images? If you just look up on mathematics and ancient India on the internet, you will find this. This is called Shena Chiti. Shena is falcon, Chiti is the altar. So, this is an altar, a fire altar in the shape of a flying falcon. Because of the light, this is not very clear, but I hope the next slides will actually show you how, this is actually a fire altar, and there are some 200 pieces. You can think of a jigsaw puzzle, okay. So, 200 pieces, all geometric shapes. You can see right triangles, rectangles, there is a small pentagon over here, and so on and so forth. And using that, they had to construct, thank you so much, they had to construct this, and there were some instruments and other things which are also put here, okay. So, what are the topics that were covered in this? For doing these constructions, you need to know something called as the Pythagorean theorem. All of us had been exposed to this probably in 8th grade or 9th grade, right, the theorem of the right angle triangle. You need to know a lot about ratio, proportion, manufacturing of bricks, and so on and so forth. So, all those things were covered in the Sulba Sutras, okay. And for what? For making these kind of fire altars, right, and these were the actuals, yeah. So, this probably is a better thing. So, you can see this is the size of a normal person, this is the size of the Chiti, and there are some layers, if I mean 1, 2, 3, 4, 5 layers, every layer has 200 bricks, so total it has to be 1000 bricks. So, with 1000 bricks they had to construct, and the design for the first, third and fifth layer were the same, and the second and fifth layer design. So, the design for the second and fourth line was the same, the design for the first, third and fifth layer was the same, but if you look from the outside, you wouldn't know what is the design inside. I don't know if it makes sense, I am just trying, right. And this was done so that the structure stays, like this interlocking bricks that we have, we don't lay bricks like this, right, it is always, in a way like this. So, these kind of systems were used, and I just wanted to show you these photos. So, this was a Shena Chiti that was used for a yaga somewhere in 1950s. You can still see that the quality of the bricks are intact. There is no cement or anything used, and there are 2 huge trees that came through that, and still it is intact, right. Here probably you might be able to see that this layer and this layer has a similar structure here. Here you have first, third and fifth layer is below the ground. They have the same, and this was another one. This is a top layer. So, this happened about 100 years ago. There was another yaga, and this is one of the Chitis. So, these photos I had a great opportunity to travel with Swami Sharadananji. I guess he would have already addressed you probably, or maybe you'll see him, right. So, Sharadanji and a couple of us, we were in Yuva Kendra, so we had an opportunity to visit this place called Panyal near Thrissur in Kerala. So, that is a yaga bhumi. So, there they were doing a yagam called Adiratram, which would go for 9 days and 9 nights continuously, and there would be priests from different places of different age groups. I think the youngest one was some were 8 or 9-year-old priests, and there were many older priests as well. And there were people from Nat Geo, BBC, all of them to take documentaries of the entire thing. And it says, it goes like, if you do the yaga properly, at the end of the 9th day, you burn the yagashala, okay. So that's how the yaga ends. And if you do it properly, it will rain, and that rain will extinguish the fire, okay. And this is not old times, and this is where I actually visited. And this was done in the month of April, not in the rainy season, just to, be lucky. And it actually rained after 9 days, and it was there in the newspapers as a small, item of news that something like this happened and so on. So all these things that made it happen, or to do that, there was a lot of math element attached to it. So students, when they were learning all these texts, they were not learning mathematics they didn't have a different period for mathematics. Math was something that they were learning along with a lot of other subjects, okay. Right. So coming to Bodhayana, his exact place is not very clear. So this is today. I'm sorry about the date. This timeline I just copied from a previous presentation. So we have moved a little ahead, okay. And this is Bodhayana's time, okay. And while doing this, he would have definitely encountered something like this. So if you have a right triangle, or imagine a square with side 1 unit, what will be the length of the diagonal, okay. All of you remember back in grade 9, square root of 2 is irrational. Probably that was the first proof that we would have done in number theory. So today we know that this is an irrational number. That means you cannot express this precisely in a decimal form. It will, it will be 1.4142, and it will just go on forever. It won't stop anywhere, okay. So how do you find the exact value for this particular thing is a natural mathematical problem that he would have faced, right. So how does Bodhayana give the value for square root of 2? And that is very interesting, okay. So this is the sutra that he writes. He says pramanam is 1. So a lot of words were used for numbers, like pramanam. There is one pramanam, Veda pramanam. So 1 refers to pramanam. Tritiyena is 1/3. Tad chaturthena, that means 1/4 of that, tad. Atma chaturstrimshena, so Atma is 1, chaturstrimsha is 34, 1/34th. Unena, that means you subtract from that, you do simplify all these things, and finally you get a fraction which is 577 over 408, and that gives you the value of square root of 2 approximately, okay. When we see this from a math background, I mean, why does he have to do all these things? Why can't he just say that it is 577 over 408, right? Or why didn't he say that it is 1.4142156686? Why didn't he give this particular value? What do you think? It gives some insights into the derivation. That's exactly the reason why he writes in this way. Not just that, so this is a sutra literature, okay, Bodhayana Sulba Sutras. So sutras are kind of very cryptic. You would have realized that by now, right? So he gives this in the form of a sutra, and this also gives a geometric way of looking at deriving the value of square root of 2. There are a lot of research papers written on this particular thing, and you get a finally you get a fraction. Okay, so this is not what Bodhayana gave. Bodhayana gave this. My question is, why do you think Bodhayana did not give this 1.4142? Why did he stop at 477 over 577 over 408? Number of bricks required for a yaga, okay. Okay, he didn't want to reduce it, but the fact that we write it 577, 408, it becomes rational. So it is not. Alright, so I will not torture you more. Okay. So the representation in this form did not exist at that time. It was only representation in terms of fractions that were used at that particular point of time. So this is how we see, okay, when did decimal place value system come into existence, right? So from text, this is how researchers arrive at these kind of things. What is also interesting is he uses a word savisheshaha. This is a grammar test, Sanskrit grammar test. Your teacher is sitting there, right? So pressure on all of you. Just joking. So what do you think this word savisheshaha might mean? Of course, you use different grammar rules, it can mean a lot of things, but there remains something. That means you do all these things and still there is some small unit that remains. So what he is trying to say is, this is not the exact value, it is only an approximation. I get goosebumps when I talk about this. So we are talking about square root of 2 is irrational. Irrational numbers was discussed in the Western world somewhere in the 18th, 19th century. They accepted that there exist irrational numbers. Till then they were called nonsensical. No, they cannot be counted as numbers. And here we have somebody, I wouldn't claim that they were talking about irrationality, but he knew that you cannot arrive at the final result because of this word savishesha. So in a conference that I had gone to, there was one talk just on this word savishesha. That was the entire talk on. Yeah? And he said, why savishesha, why not something else, and so on and so forth. Okay. Alright, so let's move a little forward. So we are 1000 to 800 BC, now we are around 300 BCE, which is Pingala's time. Pingala, what text did Pingala write? Chandas. Pingala wrote the Chandas Shastra. Okay. And in that he was dealing with these two syllables, Laghu and Guru syllables. And Chandas, as you know, deals with rules for writing poetry, right? Rules, you know, the metric forms and all those things. And while he was doing that, he came across, or probably a mathematical thought struck him. He said, if I want to make a meter with 4 syllables, right? I can form it with all gurus, all 4 syllables can be gurus. I can form it with all 4 laghus. I can form it with 2 gurus and 2 laghus. That could be guru, guru, laghu, laghu, or it could be a guru, laghu, it could be a laghu, guru, laghu, it could be different things, right? So he said, let me explore this further, and he asked these questions. He said, how many combinations can exist in a 4-syllable list, or a 5-syllable list, or a 6-syllable list? And if we talk in terms of mathematics, we talk about, can we generalize in an n-syllable list? Can we come up with a formula to do that? Then he said, once we know how many are there, is there a way to list everything down in a proper sequence? Okay. Then can we find, if somebody tells you a particular pattern like guru, guru, laghu, guru, in that sequence can we instantly say which row number it will come? Or if somebody gives us a row number, can we figure out what is the pattern without listing everything? Right? Anybody from a computer science background here? Right? So these are topics that we generally do in second year, third year algorithms course at an undergrad level. Probably if we follow the famous textbook of Tardos and other people, we'll find these kind of listing algorithms, sorting algorithms, finding the rth row of a n syllable and so on and so forth. So these algorithms were discussed. The earliest available work is Pingala's work, that is around 300 BCE. And these are actually programs that some of these are used even today. Not knowing that this was done by Pingala. Okay, so somebody independently came up with these algorithms, but they did not know. In fact, I was attending a course maybe around 5-6 years ago on algorithms, and there was another student with me with whom I had done this course on Pingala's Chandas. So we two were sitting. My programming background is not good, And this guy was good in programming, he was a 10th grader, and there were 4 problems or 4 codes that were given on the screen saying that these are 4 ways in which you can find 2 power some number, any number. And the question was, which is the most efficient algorithm? And the answer was some option, probably B or C. And this boy immediately remembered, he said that particular algorithm was Pingala's algorithm to find 2 power n. And we told the professor that, this algorithm is very old. He said, oh, is it so? This is one of the most optimum algorithm to find the power of 2. I mean, I am not trying to just throw some math or computer science over here. What I am trying to say is, these are algorithms which are extremely efficient. Of course, there were no computers at that point in time, but these algorithms that they came up with were very efficient algorithms to execute. Okay. So this is the list. Alright, so let's have some fun time. Do you see any pattern in any of these? I didn't have much space, so I just split this second half to the right. Yeah, yes. Yes. Yeah. There is Guru, Laghu, one Guru, one Laghu, one Guru, one Laghu, one Guru, one Laghu. 2 Gurus, 2 Laghus, 2 Gurus, 2 Laghus. 4 Gurus, 4 Laghus. 8 Gurus, 8 Laghus. Yeah, it increases by the power. This is 2 power 0, 2 power 1, 2 power 2, 2 power 3 and so on. Right? And this was Pingala's algorithm. Pingala said even a dull-witted person will be able to execute this algorithm. That is what he said. You can just use that, right? Anybody can do that. And you will get 16 combinations for 4 syllables, and this is how you can list it. Using this listing, he said, this is how we can find. So he gave rules for finding that 10th row, 9th row, 8th row, whatever. And if somebody is giving a particular row pattern, we can find the row number and so on. But these rules, they cannot be just tricks, right? I mean, the question is, how did Pingala come up with the mathematical rules? See, one is you have a rule for listing. Then you are saying in that list you want to find which row this particular pattern will come. So all these things has to have some mathematical structure which will give us formulae for doing all these things, right? So how did Pingala come up with this is a genuine question that any student of mathematics will ask, or anybody might ask. And did he, sit and meditate in the forest? What did he do to come up with these kind of things, right? So this is what he did. He replaced all the gurus with zeros and laghus with 1. Okay. And what we have here are numbers that we call as the binary numbers. Okay. But as you can see, they are not sorted in the natural order. So this is all zeros, but this is not how you represent 1 in binary. Okay. This is not how you represent 2 in binary. But if you take the mirror image of these, for those of you who might have learnt binary, 0, 0, 0, 0 is 0, 0, 0, 0, 1 is 1, 0, 0, 1, 0 is 2, 0, 0, 1, 1 is 3, 0, 1, 0, 0 is 4 and so on. So it gives a binary sequence in the natural order, and that is what helped him to come up with all these rules. We are talking about binary mathematics, about 300 BC, which is like 2300 years ago. Okay. Now somebody can still say, oh, maybe it is just a coincidence, how do we know if this was true and so on and so forth, right? So let's just take, I'll get there, but before that let's just take a look at Pingala's work, right? So, and generally when we hear all these names, at least I used to think, oh, that was one great genius mind and nobody before him or her was genius, and after that also nobody. So one person invented or contributed everything, right? Generally when we attribute something to somebody. But we can see that, in works by Charaka and Sushruta also, which was prior to 5th century BC, it contained this topic of permutations and combinations. Pingala, yes, comes here. Pingala of course makes a significant contribution. And then this is BCE, this is Common Era, okay. So this time period itself is somewhere around 8 to 900 years. Varahamira, who is an astronomer, he comes up with, he extends Pingala's work further. Virahanka, who also deals with music, he also extends Pingala's work further. Kedara, he also does that. Hemachandra, 12th century. Sharangadeva, famous, those who are students of music would have heard of Sharangadeva's work, Kashmiri Pandit, and his work is today used in learning theory of music, dance and percussion instruments, Narayana Pandita and so on. So what do we see here? We see a good lineage of research happening, there is, and everybody did not do something completely different from what Pingala did. Pingala started off with some algorithms, others just took it one step ahead, and by the time it was Narayana Pandita's time, there was phenomenal work that was done in just that particular discipline. And this is something that I found quite inspiring, because today when we talk about research, right, we think, okay, research is something that is happening today, but here we can see research was happening, since millennia. Alright, this is famously called the Pascal's triangle, all due respect to Pascal, Blaise Pascal. Around 17th, 18th century, he popularized this particular triangle. It can be used, it has a lot of mathematical application to that, we will not get into that. But this triangle is what Pingala calls as the Varnameru. Varna is referring to color, so Laghu and Guru are looked at as two different colors, okay. And using that, if you want to, so we had seen 16, no? So if you are having, how many combinations can you make with all Gurus? Only one combination. How many with all Laghus? Only one. How many with 3 Gurus and 1 Laghu? 2 Gurus and 2 Laghus. 1 Guru and 3 Laghus. So you get all those numbers over there, right. Just look at the time difference. 2000 years, not 1 year or 2 years, okay. Alright. Okay, so coming to Chanda Shastra, this is one sutra that he writes for making that Varnameru. He says Pare Purnamiti. Over. Gone to the next sutra. But what does this Pare Purnamiti even mean? Right? So to understand all these things, we need commentaries. So this was a commentary written by somebody named Halayudha in the 10th century. So 10th century, somebody is writing a commentary to something that was written in 300 BC. So 1300 years later also people were writing commentaries of a particular text, right. And the commentary itself is quite elaborate. In fact, it is very interesting. We see commentaries of commentaries in many texts, because the commentary itself is very hard to understand. So there is a commentary to a commentary. And I have seen a commentary to a commentary to a commentary to a commentary of a text. 4 commentaries, because for us mortals we need, even more simpler explanation. Okay. Alright. So this is Pingala's algorithm to find 2 power n. We will not get into the technicalities of these, but let's just read this, okay. Dvirardhe rupe shunyam dvishunye tavadardhe tadgunitam. Is there anything that strikes you in this, or something that you are familiar with? Some word. Shunya refers to 0, right? What is popularly heard? Who discovered or invented 0? Popularly, Aryabhata. Now what was the time period of Aryabhata? Aryabhata was around 5th century. 476 AD, he was born in 476 Common Era. This is 800 years before Aryabhata. You see the word Shunyam. So what he does is, he actually uses a symbol for 0 and he uses 0 as a digit. So what I said earlier is, when Pingala uses binary mathematics, where is that 0 coming from? 0 is coming from his own work. So he he says, okay, do this particular process and finally you can find 2 power n in an optimal time. So, I will be happy to discuss on this maybe after the session if there is anybody interested in going into some technical aspect over here. But for now, let us just mark this and let us move ahead to development of 0, right. And this is where I think in many places when we read, okay, Indians discovered 0, Indians invented place value system, we feel really proud about it. What are we proud of? Indian discovered 0, so what? Or did others also talk about 0? Did others talk about place value system? Did they talk about decimal system? I mean, how does our work become so special, right? Without knowing that, if we say I am really proud that Indians discovered 0, it is like saying my grandfather had 13 elephants, I don't own any, I have no idea about any of these things, right. So, at least we should have some idea about how things were happening. So, let us get into the Egyptian civilization. Again, Egyptian civilization is a time scale, mind you, not one particular dot, right. So, they were using a blank space to represent nothing. So, they had an idea of 0 as nothing, and if they had to represent nothing, they will use a blank space. But the problem is when you say blank space, this is a blank space or these are 2 blank spaces. We don't know, right, because blank space there is no length to a blank space, okay. They were using a symbol like 0, but that was for representing the fraction 1 by 4. So, if we see a symbol 0 in any of their work, it is not the 0 that we mean today, but it is 1/4. And this is how Egyptians use. So, they had 1 and you write 2 ones like Roman numerals and you do this, you get 9. For 10, they were not writing 1 0, they had a different symbol. So, they were also using base 10 in some sense. Every tens it was changing, okay, and maybe you would have seen some videos about how they were using clay tablets. So, they had stylus and they would use a stylus to put a mark on the clay tablet. So, students would carry like how you are carrying notebooks and laptops and everything to the class, they were carrying clay tablets. So, you have a pen sort of thing, stylus, and you just put a mark, okay. So, if you put that, use that to do it like this is a 1 and so on. So, they had and these were like probably this guy gave up, I am done with 1 million, right. So, they had all these symbols, and here also you can see that there is in some sense a power of 10, right, powers of 10, it is decimal, but there is no place value. I hope you are able to make the difference. There is decimal system, but there is no place value, there is no 0, okay. Let us move ahead. Mesopotamia. There Babylonians were using something called as base 60, but 60 generally when we say 60, 10 we think of the representation 60. Oh, how can you write 60 without using 0? How can we write 60 without using 0? SIXTY, right? I don't need 0 to write 60, right? Or maybe there are some symbols that would let's say this represents 60, I can use some symbol to represent 60, okay. So, they were using a base 60 instead of a base 10, and they had no use of 0 but use of blank space for nothingness. So, they were also talking about nothing and they were using a blank space for that. What about Babylonians? This is again clay tablets, okay. So, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, you make these 9 and then you tilt that thing and you punch it, okay. So, that is where you get this. So, this is a tilted version of this, okay, 10 and then 11, 12, 13 and so on. So, here also we can see a base 10 sort of thing going all the way up to 60 and then having different representations and so on, okay. Going to Greece. So, in Greece again there was no need for 0 in their system. They didn't need 0. They used alpha, beta, gamma all the way up to 9, and for 10 they used another alphabet. Went to 90, 10, 20, 30, wrote to some places again until 900. So they used 24 plus 3, 27 alphabets to, make numbers. So alpha, beta would be like alpha is 2 and beta is, so alpha's position would be something. So no, sorry, this is not alpha, this is our sigma, right? So that would be some 200 and then so on, okay? Alright. So again they did not need 0. This is very interesting. Aristotle around 4th century BCE rejects 0 from being included amongst numbers because it could not be formed, it could not be used for forming ratios, because they were obsessed with numbers and ratios and they could not form ratios with 0. He said 0 is a, not a number. We have about 500 years later, Ptolemy uses a symbol 0 with a bar on it to represent an empty space. Again, for nothingness, there was something used there, okay. So they also talked about 0, but to represent nothing. Mayan civilization, they had something like base 20 and they had a symbol for 0, okay. They had a number 0, they had a symbol for 0. In fact, they had two symbols for 0. One was if 0 comes between a number, and one was when 0 comes at the end of a number. They had two different symbols for 0, okay. Now, why am I saying all these things is just to show that how all these civilizations, they all talked about 0. So in some sense, they deserve some credit for, coming up with 0. But then how is Indian 0 different from all these things, okay? Alright, so let's also go to China. So it is said Chinese mathematicians had a lot of problems with Indian numbers. They are just paying back because we gave them a hard time thousands of years ago. Now China is paying back, okay. So they faced, Chinese mathematicians, they faced a lot of issues with Indian numbers. Why is that? Because Indian system of counting appeared in China. As we know, there were scholars who would go to different, countries. Chinese scholars would come here, and Indian numbers were introduced in around 6th century in China, and they were still using blank spaces to represent nothing until 700 CE. They were introduced to Indian thick bindu for 0. However, they did not adopt the Indian 0 symbol. The circular 0 symbol appeared in China very late in 2047. Okay. So why were they having problem? Because it's a very new system, right? They were so okay with using their existing system, but this is a very new system, so they were having trouble doing that, right? Alright, so let's come to our Indian zeros, okay. So we see inscriptions in Indus Valley civilization where there are circles used. So can we say that Indus Valley civilization had 0? No, I mean circle could mean something else, not necessarily 0. Circle is what we use today as a representation for 0. So we cannot use that. I mean, we cannot conclude. Numbers used in Vedas are not numerals. Very important, because Vedas, as you know, was an oral tradition even before writing came into place, right? So you can have a name for a number without having a form for a number, right? So what we are having like 1, 2, 3 is forms of numbers, but you can have names of numbers without having forms, right? So numbers used in Vedas doesn't mean that they were using 1, 0, 0 and so on, okay. In fact, the first appearance of 0 as a symbol to represent nothing we see in Ashtadhyayi. Okay, so there is this sutra, darshanam lopaha. That which cannot be seen is lopaha. So that which cannot be seen means it does not appear, but we can infer that it is there. Like air, we cannot see, but we know it is there, right? So adarshanam lopaha. So that, which cannot be seen. So something for nothingness is we can see in Panini's work, okay. And these are some of the what we can say, stages in some sense of development of 0. We can see Vedas containing powers of 10, but powers of 10 doesn't mean there is a 0. It is just powers of 10 names. Panini uses 0 in Ashtadhyayi. Texts somewhere around this mention the use of 0 and decimal place value system, but still things are not very clear. Katapadi number system, if time permits, we'll take a look at this very interesting system that uses decimal place value system, but we don't know when that was, discovered or invented. But what we see as a final product of application of 0 and decimal place value system is Aryabhata's text. And this is what probably the British or whoever scholars, they saw that, oh, in Aryabhata's text, you can see a proper use of 0, therefore Aryabhata discovered 0. But no, you can see that there is a 1000-year history for 0 itself. And such a profound idea cannot be discovered or invented by one person, right? It has to be just like our cell phones, right? I mean, when they came into existence, how it were, and today to what level it has evolved, right? Like my son and all, he was shocked when I would say we had a cell phone, but we couldn't take photos with that. Why did you use cell phone for? Okay, so what is 0? 0 today we use in at least these 4 sense. One is a representation of nothing, one is as a digit or a symbol, one is a origin, in x-axis, y-axis number line, and as a number, as a quantity, 0, right? So all these things is coined into one particular thing called 0, and in other civilizations they had representation of nothing, they had a digit, but not necessarily a number 0, not necessarily a place value system. So that is where India's contribution was phenomenal when it came to this. And the moment this way of doing multiplication, if you do 18 multiplied by 12, these kind of multiplication, it just, people could throw abacus and they could do computation so fast. So think about our present times, right? The moment computers came, how fast progress has been. I mean, I don't know whether whatever we want to call it is progress or whatever, but how fast things are changing, right? And that is the kind of speed that arithmetic calculations, give. So, which is why in the introduction when Sajanji was saying, the 0, the discovery or invention of 0 and decimal place value system is something that can be equal to the invention of wheel or, discovery of fire. That is how things changed after that. And that is why the whole world looks up to India saying that, oh wow, this is what you gave, right? And that is how math and science expanded in the rest of the world, okay? So we'll go to the next part, but just a small quote which I really liked from this book. Greeks could not do this neat mathematical trick. They didn't have a concept of a limit because they didn't believe in 0. The terms in the infinite series didn't have a limit or a destination. They seemed to get smaller and smaller without any particular end in sight. As a result, the Greeks could not handle the infinite. They pondered on the concept of void but rejected 0 as a number, and they toyed with the concept of infinite but refused to allow infinity, numbers that are infinitely small and infinitely large, anywhere near the realm of numbers. This is the biggest failure in Greek mathematics, and it is the only thing that kept them from discovering calculus. So when we say how is it that some civilizations were able to come up with these kind of things in mathematics, what stopped them? Sometimes there are these fundamental things that as mathematicians, as humans, maybe they miss, and they miss to come up with something really amazing in mathematics. Okay. Alright, coming to Aryabhata 1 and 2, the next sections are kind of a little fast, so I'll just take it. So Aryabhata 1, he wrote Aryabhatiya when he was just 23, okay, 23 years old. I mean, 23, and that text is something that we can, that manuscript we can just fold and put it in our pocket and go. I mean, that's how small some 108 verses or something, that's about it. And that contains a lot of knowledge about trigonometry, about geometry, about place value, and of course some arithmetic calculations and things like that. It also contains theories. So for instance, he was the first person who said that the earth rotated around its axis, which is non-trivial, because when you look up in the sky, there is no way that you can figure out that earth is rotating, if you have no other knowledge, right? It is non-trivial. So he came up with this phenomenal theory, and he was the first person to come up with that. And he also came up with things like this. So again, let's try to decode this, okay? Chatur adhikam. What do you think chaturaha? 4. Adhikam, excess or more. Shatam, 100. So chatur adhikam shatam. How much is it now? 104. Ashtagunam times 8. Okay, so do it. 104 times 8. 832. Okay. Dvashashti. 62. Sahasranam. 1000. 62,000. Okay. So you add this. What was the first number that? 832 plus 62,000 comes to 62,832. Okay. Ayutam. 10,000. Okay. Dvaya. Twice of that. So 20,000. Okay. Vishkambha. No clue. Vrittam. Vrittam is circle. Parinaha. Circumference, actually the boundary. Okay. Vishkambha is diameter. What do you think he is trying to give? The value of pi. So he is saying if you have a diameter of 20,000, then the circumference will be 62,832. And he is giving this in Aryameter. And those of you who know to chant Aryameter, you can chant this. Okay, no test, no pressure. Okay. Right, so he gives this, and again he uses a word asannaha. What do you think asannaha means? Not asana, asannaha. Asana is again approximate or close to. So he also does not miss to say that this is only an approximate value, not the exact value. Why? Because again pi is irrational, not a rational number. Okay. And he gives this. So Aryabhata, people say Aryabhata gave the value of pi approximately up to 4 decimal places, correctly up to 4 decimal places. But I think that is only 50% of the credit. The rest of the 50% is saying that this is approximate, that this is not the exact value, and that requires a mathematical genius, and not just saying that okay, I 3.1416 and it ends there, right? And then he also comes up with areas like solving linear indeterminate equations, which is again something in number theory, using a process called Kuttaka. Kuttaka is like Kuttanam, Kutna, pulverizing basically. So this method became so useful. It was used for some calculating which day certain planets will come in one line and so on and so forth. So when you have 2 variables and 1 equation, how do you find that, and so on and so forth. Okay. So this is in a nutshell about Aryabhata 1. Similarly, we have Brahmagupta. Okay, another phenomenal mathematician, sadly not as much known as Aryabhata, but Brahmagupta, he came up with a lot of new things. He came up with rules for operations with 0. Like we have found 0, we are using 0, but what happens when you multiply by 0? What happens when you divide by 0? What happens when you add something with 0? And he also came up with negative numbers. Okay. So negative integer, what's the big deal? Negative numbers below 0, it has to be -1, isn't it very natural? No, it was not natural. Okay. And he came up with rules for negative integer, negative times negative is positive, and so on and so forth. And he formalized algebra, and another great contribution of his was something called as Bhavana process to solve a Varga Prakriti problem of the form x square minus dy square equal to 1. Have you seen this equation anywhere? Yes, right. On my t-shirt, right? So this, I'll come to what is so special about this particular equation in a bit. So he came up with a process and nobody had started thinking about such hard problems. This is a very hard problem, okay, not trivial at all. And this is again 7th century Common Era, okay. Let's move ahead. So now we move ahead from Brahmagupta's time to we have 17th century, a famous mathematician. In fact, Fermat was a lawyer, a French lawyer, and math was something that he was naturally good at, and he used to pose problems to the mathematical community back then. So in those times during the Renaissance period in Europe, they were not collaborating, they were always competing with each other, the mathematicians. They would challenge each other. Now I challenge you. So he said, if somebody can solve this particular equation, x square minus 61y square equal to 1, he says to arithmeticians, that is mathematicians, I propose the following problem to be solved. And he said, if somebody can solve this equation, what do you mean by solve this equation? He said, can you find the smallest integer solution? In fact, non-negative integer solution for x and y. So x has to be a natural number, y has to be a natural number. Can you find the smallest integer solution for this? And he said you can do it in 1 year's time. So that hard this problem was, okay, and Fermat posed this problem, okay, and let's see what happened. So this problem in the West is called Pell's equation. Pell was another mathematician, and the story is also very interesting. So there was a third mathematician named Euler, E-U-L-E-R. If you have done some engineering math or math, you would have heard his name. Euler, we call his name in a very different way in India, but his name is pronounced as Euler, one of the greatest mathematicians of all time. So he was working on this particular equation, x square minus dy square equals 1, and in the book that he was referring to, he saw something with a double L, okay. So there was another mathematician named Wallace, W-A-L-L-A-C-E probably. So he thought this was Pell. Pell was another mathematician. So Euler said this is Pell's equation. He called this as the Pell's equation. But Pell had nothing to do with that equation. But when Euler is saying, nobody dare question Euler, okay. So they all accepted it as Pell's equation, but Pell had nothing to do with this equation. So there is a misnomer. So what is this equation about, okay? I am going to do a little bit of math, okay. So just bear with me. Let's say x and y are natural numbers and x square minus 2y square equals 1. Suppose the value of d is 2, right? If we do some bit of trial and error, we can get that, if you put in 3 and 2. So x is 3, 3 square will be 9, 2 square is 4, 4 times 2 is 8, 9 minus 8 is 1. So we say 3 comma 2 satisfies the equation. So this is the smallest integer solution. You will say, you said this is a very hard problem, this is very easy, 3 comma 2 we got it instantly, not a big deal, right? Now with 3 comma 2, the question that Brahmagupta asked was, can we find the next solution? Okay, from 3 comma 2, can we find the next possible solution? And the next possible solution is 17 comma 12. That is when x is 17, it becomes 17 square. Anyone wants to remember? 289. Okay, 289 and 12 square is 144, double of that is 288, difference is 1, so satisfied. Okay, 99 comma 70 also satisfies this. 70 square is 4900, double is 9800, this is one more than that, okay. And the next value is 577 comma 408. Now it is not about the solutions, but how Brahmagupta gave a method to generate all these solutions, that has to be commended. And this is when the world has not started using algebra. This is the kind of algebra that he does, not solving linear equations in one variable. 3x plus 4 is 7. What is the value of x? No, not those kind of math, right? Very intense math, okay. Anyone remembers this? 577 comma 408? The square root of 2, what Bodhayana had come up with, right? Through a different way, and here it is 577 comma 408. So if those of you who are using a laptop or anything, you can just punch in these values. 577 upon 408, you will get square root of 2, approximate. 90 upon 70, what value do you see? Anyone wants to try 90 upon 70? Yeah, I know, even to take out the device and punch the numbers in is very hard, let alone do it in our head, right? So 3 upon 2 will give you 1.5, 17 by 12 will give you something close to 1.4, this gives you 1.414, so this is correct up to 3 decimal places, this is correct up to 4 decimal places, and this goes on, okay. So this is what Brahmagupta had come up with, but he was stuck somewhere, no. He said, I know how to solve this for some particular values of D, but not all values of D. So this D here, it has to be a non-square number, but I don't know for any number how to solve. So he started that. But then, as I was saying a little while ago, right, research was something that was always there in India. So in about 500 years time, Bhaskaracharya the second, okay. So he was posing problems, and during this period there was a lot of work related to this equation or this particular area of mathematics. And this equation, if you remember, was the same equation that Fermat had posed to solve, okay. Fermat's time period was 17th century, Bhaskara's time period is 12th century, about 500 years gap. Okay. By the time of Bhaskara and Sridhara, another mathematician, they had come up with a method to solve this particular problem for any value of D. Okay. And you know what is the smallest solution for this? Any guesses how many digits for in x and y? We saw when D was 2, the smallest solution was 3, 2. For this one, the smallest solution is 1,766,319,049. This is the smallest value that you can get for x, this is the smallest value that you can get for y. Done by hand, okay, in 12th century. Right? So when we say these people were great, I mean there has to be something with which we can compare and appreciate, to what extent they were involved in mathematics, to what extent was their expertise in math. Right? This is a famous historian mathematician who made this remark. What would have been Fermat's astonishment if some missionary just back from India had told him that this problem had been successfully tackled there by native mathematicians almost 6 centuries earlier. Right? The same problem, not even a different problem. Right? So this is the kind of richness that we see in all these texts. We will go to something more. I will give you some sample of Indian, some sample of other problems also, but let us also get into this particular aspect. How do we know when a text was written? Okay. So when I was discussing with Swamiji, Swami Advayananji about this particular session, so I asked him, what do you expect me to come and share with everybody who is interested in Vedanta, right? He said, share with them something that everybody ought to know, and there has to be some reference that we can always go back to when if somebody is questioning us or if we are talking in a forum related to mathematics. So how do we know when these texts were written? Is there a particular way in which we can find these dates? Okay. So there we see two systems, one is Katapadi, the other is Bhuta Sankhya. And these were systems that were used for mentioning the date on which a particular text was written in the text. Not always, but sometimes. That is why for some texts we don't know when it was written, we have no idea. So we say we don't know. That is a problem that we face today, right? So Katapadi rules are pretty interesting. Says every consonant is given a number. So this is the chart, okay? I mean, all of you know the Varnamala, right? Ka, ka, ga, ka, nga, cha, cha, ja, cha, nya, ta, ta, da, ta, na. And so ka, ta, pa, ya, Adi, that is etc. or starting with Katapaya. So any of these Katapaya can get the value 1, these can get 2, for 3 you can use any of these, 4 any of these, 5 any of these and so on. Okay. Every consonant is given a number. If a vowel is used separately, it is considered as 0. So if I say Anand, right, let's say Anand. So A is used separately, this is 0. Na is, we'll have to see this as Na plus Okay. What is the value of Na? Na is 0. It is combined with a vowel, so this is 0. The is actually the plus a. So the next one says, third one, the consonants which are not combined with a vowel do not have any weightage, are simply ignored. So this is combined with a vowel, so it cannot be ignored. What is the value of the? 8. Okay, 0, 0, 8. Now fourth and final rule. The rule applied in writing the code was Ankanam Vamatogati. Digits or numbers move in the left direction. That means once you have written this, you have to read it the other way around. So if you have to write 800, I can use a meaningful word Anand. Right? Let's try with your names, okay? So give me one name. Okay, I know one name, Sajanji. So I'll write okay, I mean, forgive me for all the visargas and everything. I'm just keeping it very simple. So Sa 7, 8, 0. So you reverse it, it is 0, 8, 7. So if I have to say 87, I can say Sajan. I mean, it won't be Sajan, it has to be, Sajanaha, or maybe I can make it as Sajjanaha. Okay. Why? Because this will not be 8, 8. This is J plus A. And you might want to recollect the third one. The consonants which are not combined with a vowel do not have any weightage. So this is not combined with a vowel. So this is ignored. This is combined with a vowel. Combined in the sense followed by vowel. So this will have value. So when you say Sajjanaha, that also represents 87. So you can make a lot of meaningful words to do this. And they would coin these kind of phrases at the beginning, let's say in the invocation verse or in the last line of the text. And many a times that would actually be the historical date when the text was composed. Okay. Ji. Oh, in other languages, not Sanskrit. Okay. Okay. Na plus E, right? Na plus A. Okay. So all that we are concerned is the consonant followed by a vowel? Yes. Is the consonant followed by a vowel? Yes. Is the vowel independent like Anand? Is it independent? No. Vowel is here in Ni or Na, the vowel is not independent, right? So we just take the value of the consonant. So here it is 0 followed by vowel. So Na, Ni, Ne, Nai, No, Nam, everything is 0. So there you can make any form out of those. Okay. Any other names? Let's see who do you think in your batch is going to be the top scorer in terms of the numbers? Sorry? And what's no way, nobody can beat that. Okay, so alright, let's try. You all should try, okay? So how do you say that? Sorry? Channa Basava Deva Ru. Okay. All right. Exercise now. Cha. 6. 0. 3. 7. Your alawa 4. The 8. Your alawa 4. Ru. 2. Okay. 2, 4, 8, 4, 7, 3, 0, 6. 24,847,306. So you can try for all these. So when we do these topics in the camps, no, children are really fascinated. And some of them have come back saying that, you know what, we actually used this when we went back. I said, how? We were playing cricket. Okay, they were playing cricket or football or whatever. And instead of saying whom to pass the ball to, because the other team should not know, they used the first 2 letters of every name and made a 2-digit number for everybody. So everybody knew. They taught Katapadi to everybody in the team. They said, this is how we can remember each other's names, right? And then they used it, right? Okay. Let's see where this was here. So, Ayur Arogya Saukhyam is the last word in Narayaniyam. Narayaniyam is a famous text in Malayalam. And the last word is Ayur Arogya Saukhyam. And as the word goes, we might think, oh, it's just a prayer, Ayuhu, Arogya Saukhyam, you know, for well-being, long life, good health and all that. But when you decode it with Katapadi, it gives you a particular number, and this actually translates to the date on which that text was completed. Okay, so that is something. So knowing this system is very important to, you know, kind of find out when some texts were written. So it was either Katapadi or Bhuta Sankhya that was used. Okay, so this is another verse from a mathematical text where they used to write the value, you know, code the value of pi. Okay, Bhadram, Bodhisiddha and something, it goes on. So when you read it backwards, it is 3.141592653. It gives the value of pi correctly up to what? Maybe 15 decimal places or something. To remember that value, they were making these verses. Another area is in music. So in Carnatic music, there is Melakarta ragas, and there are 72 Melakarta ragas put into. So there was this person, Venkatamukhi, if I am correct, Venkatamukhi. So he came up with Melakarta ragas, right? So he gave the 6x6 grid, so 36, and every cell is divided into 2 parts. Let's call it upper and lower part. Okay, and you can see that here whatever comes in blue is Shuddha Madhyama and whatever comes in red is Prati Madhyama. So there are 2 mas, and for Da there are 3, you know, I am just calling it as D1, D2, D3, and similarly for Re there are 3 nodes for Re and 3 nodes for Ni, Re and Ga. So if you take any particular cell, let's say that second row, 4th cell. So second row, 4th cell is 10 and 46. Okay. So if you know the name of the raga, so in 10 it is Nataka Priya. Okay, Nataka Priya. Now let's use Na. What does, okay, now there is no reference. You have to think from your memory. Nata. Na refers to 0. You have a cheat sheet here, huh? 0. And Ta refers to Kata, right? 1. Reverse it, you get 10. So what? So if you remember the name of the raga, you can know which is the cell position that the raga will come to. And if you know that 10 comes there, you just have to look up, oh, this is Da 2. You look down, oh, this is Ni 2. Look left, this is Re 1. You look right, it is Ga 2. And it is in blue, so that is Shuddha Madhyama. So there you have got the Arohanam and Avarohanam of the raga. So you know which are the swaras that would come here. All that you need to do is remember this particular chart. I used to think, I used to wonder who gives names for all these things. Is there some supreme authority who gives names for ragas? Because what is the idea behind this? But if you look at all these names of Melakarta ragas, they are given so that they fit into that particular cell in Katapadi. There is no meaning, there is no logic behind all these raga names. It is just given in such a way that you can fit into this particular structure. Okay. Alright, coming to the last part, what is the relevance? Why should we do all these things today, right? Very eternal question after who am I? Second question is why should I do math, right? So why should I do this, right? So just to give you a glimpse, okay, so this is a very interesting problem. Just try to make it interesting with some colorful images. Out of a heap of pure lotus flowers, 1/3, 1/5 and 1/6 were offered to Shiva, Vishnu and Sun. A quarter was presented to Bhavani. The remaining 6 lotuses were given to the preceptor. Tell quickly the whole number of lotuses. Quickly. Okay, we can ignore the word quickly. Now this is a problem from Leelavati. Leelavati is a text written by Bhaskaracharya. I think you would have seen in Upanishad Ganga screening. So this is a problem from Leelavati, and the way the problems are presented is it's kind of, you feel like doing it, or there is some context to it. It is not just mathematical expressions. Okay. Another one, out of a herd of elephants, half together with 1/3 of itself were roaming. So half and 1/3 of half were roaming in the forest. A 1/6 plus 1/7 of itself were drinking water. 1/8 and 1/9 of itself were playing with the lotuses. The leader of the herd was seen accompanied by 3 females. What is the number of elephants in the herd? These are technically middle school level problems, okay, but we dare not put these problems in today's textbook because they will find it extremely challenging. But just look at the level of problems that they were doing and the way in which these problems were kind of coined. And there are again some interesting problems, like there are 2 monkeys, pardon me for the drawing with mouse. There are 2 monkeys sitting on a tree. They saw a fruit and they want to get to the fruit. One monkey climbs down and goes to pick the fruit. There is another adventurous guy who jumps up in the air and glides down through a creeper to get that. The distance covered by both of them is the same. This guy who got down 100 feet or whatever, and this is 200 feet. So the blue distance is also the same. Can we find out the height of this jump? Right? So this is a geometry problem that is presented, but you cannot solve it without using algebra. So that is a kind of problems that Bhaskaracharya and many others bring. It is a perfect marriage of geometry and algebra. Unlike when we learnt geometry and algebra, it was completely different. These were, you look at the problem, this is a geometry problem. Look at the problem, it's an algebra problem. There is no mixture. Yeah. Similarly, this is another famous problem, snake peacock problem. There is a peacock sitting on a pole 9 cubits high, and a snake it sees which is 27 cubits away. Both of them travel at the same speed and the peacock catches the snake. We need to find out how far was the snake from the bottom of the pillar. Okay. So they would create all these characters and kind of make this interesting. Of course, today if we have to present it to students, we cannot bring a snake and a peacock. Maybe we will have to think of Batman and some other Marvel comics or DC comics heroes and things like that. But at least we have some ideas that we can borrow from these texts. Okay. Last 2-3 slides. So all these up to Bhaskaracharya was 12th century, and it was believed that there was nothing much in mathematics that was happening in India after the 12th century. Until maybe 100 to 200 years back, there was a British officer who came up with some Malayalam manuscript of mathematical texts, and that is when they slowly started figuring out that there was an entire school of mathematics in Kerala, which is called Kerala School of Mathematics. You might have read in the news at some points in time there is a mathematician named Madhavan. His work in calculus was phenomenal. He came up with the ideas of calculus before Newton and Leibniz. So that is true. Madhava's time is 14th century. The Golavit Madhava, sorry about the small fonts at the top. His student was Parameshwara. Parameshwara's son as well as student was Damodara to the left, and Damodara's student was Nilakantha, who was also Parameshwara's student. So there is a lineage of mathematicians that you can see from 14th century all the way till 19th century. So math from the IKS was still prevalent in India until 19th century, at least in the state of Kerala. And this is where a lot of contributions related to calculus and further advancement in trigonometry and astronomical aspects were given during this time. Okay. So whatever we have seen so far comes under what I was saying as ancient Indian mathematics or mathematics from the Indian knowledge systems. But today we know something popularly called as Vedic mathematics, right? We see ads on YouTube, Facebook, all the Vedic maths, learn Vedic maths and so. So that does not come under whatever we have discussed. Okay, this is an independent subject contributed by Shankaracharya Swamiji. His name was Swami Bharati Krishna Tirtha. He came up with some sutras 100 years ago. And those sutras, using those sutras, you can do arithmetic calculations and algebraic calculations fast. Okay. So that is an independent contribution. So that he called it, or probably the publishers called it Vedic mathematics posthumous, because he wrote the manuscript, he passed away in 1960, 1965 the book comes with the title Vedic mathematics. So there is a lot of debate about this. This is not Vedic, how do you call it Vedic, because you don't see this in Vedas and all these things. There is a big debate about all these things, but if you keep that debate aside, the subject is very useful. You call it by whatever name, the subject is useful. But when we look at mathematics, we should not think, oh, Vedic mathematics or Indian mathematics was only this arithmetic calculation. That is only this small part of mathematics that he contributed to. Okay, alright. So what can we see? We can see a line of research that has been happening in India, and which shows that the way in which knowledge was transferred and passed on was very methodical, and people were interested in taking it ahead, and there were a lot of scholarly work that was happening, not independent discoveries that people were making. Another interesting aspect and a very important one in Indian mathematics is it is very algorithmic, algebraic and generative in nature. So what do I mean by that? Generative, I am sure you would have had sessions on Ashtadhyayi, right? So using those sutras, you generate rules, right? So those generations, so in mathematics also you can generate new things. So some parts of the chandas have this generative nature, and everything is algebraic. All the place value system also is completely algebraic. So if you say 234, it is nothing but 2x square plus 3x plus 4, where x is 10. Right, you put x as 10, this becomes 200 plus 30 plus 4. The reason why we are able to do these multiplication arithmetic calculations is because it is based on algebra. So algebra is like the backbone of Indian mathematics, and we can see that everywhere, which is not seen in Greek mathematics, for example. They were obsessed by geometry, right, but their skeleton was more of logic, and our skeleton was algebra. And lot of algorithms, because for doing any procedure you need algorithms. How do you do this, how do you do this? So that is why we see a lot of algorithms or procedures in Indian mathematics. In fact, whatever we learn in school, like this multiplication, division, square root, all these algorithms come from Indian tradition. We can also see a good collection of math problems which we can introduce into the class. So that is where my research is. So I am doing my research from CVV, trying to see how these problems are relevant to modern day classrooms and how we can use them to identify talents in the class, how we can use that for improving their thinking skills in the class. And we also see that math was always learning was always interdisciplinary in India. In fact, until the 8th century, there was no separate book on mathematics. Math was always along with something else. So math was always applied in India. Nobody was doing math, I don't have anything else to do, okay, let me do some math. No, they were doing math for achieving something. So there was always a real life motivation for them. And today what we need is, of course, there is a lot of research happening in all these texts, but many or most of the research is happening from a humanities perspective. Critical edition of the text, on commentaries and all that. All that is very important. But we also need people with a strong math and science background who can see where this is useful today. Because unless and until we can show relevance, most people may not buy it, right? And that is where many people, in fact, today we have a lot of people from top institutions in India who are top class researchers in history of mathematics in India. Their domain is physics or mathematics or computer science, but they have been contributing immensely. Okay. So, small list of very well known mathematicians from Bodhayana to Shankar. This is not an exhaustive list, but whenever somebody is asking name a few mathematicians in India, thanks to those two satellites that they named after Aryabhata and Bhaskara, we know two names, but there were many more, and we should know at least a few names, who and what were they really responsible for. Okay, so I think I'll just take a pause over here. I think I shot over time a little bit. I'm sorry about that. So yeah, thank you. Om Purnamada Purnamidam Purnat Purnamudachyate Purnasya Purnamadaya Purnameva Vashishyate. Om Shanti Shanti Shanti. Hari Om Shri Gurubhyo Namaha. Hari Om.